This problem is based on the static equilibrium. We have to find out the magnitude of the forces which keep the object in static equilibrium. Let us read the problem. The drawing shows a uniform horizontal beam attached to a vertical wall by a frictionless hinge and supported from below at an angle 39 degrees by a brace that is attached to a pin. So this is the hinge, and then the beam is attached to a wall, and then the brace is at an angle 39 degrees, theta 39 degrees, attached to a pin. Okay. And then the beam has a weight of 340 newtons. The beam's weight is 340 newtons. And then three additional forces keep the beam in equilibrium. The brace applies a force P bar to the right end of the beam that is directed upwards at an angle theta with respect to the horizontal. That I drew here, this one. And then the hinge applies a force to the left end of the beam that has a horizontal component H and a vertical component V. Find the magnitudes of these three forces. This is the forces applied by the hinge, horizontal and then vertical. And then the base is applying a force at an angle theta is equal to 39 degrees. So we have to resolve the force into two components, vertical component and horizontal component. Now, the first law is to keep the object in equilibrium, the sum of the torques must be equal to 0. That means clockwise torque must be equal to counterclockwise torque. That I will write. Sigma torque is equal to 0. This implies clockwise torque is equal to counterclockwise torque. Here the beam is applying the torque in the clockwise direction, whereas the pin is applying the torque in the counterclockwise direction. So here torque beam is equal to torque pin. So the beam, what is the torque applied by the beam? Force times distance. Here the force is nothing but its own weight, that is Fg, and then distance is this is a symmetric one. So for the beam, the force acts at the center point. So if the length is L, let us consider L be the length of the beam. So I will write here, let L be the length of the beam. Okay, so Fg acts at L by 2. And then theta is equal to 90 degrees. Therefore, torque is equal to Fg sine theta times L by 2. Okay, here theta is equal to 90 degrees. So torque will become, torque beam is equal to Fg L by 2. And Fg is given as 340 newtons. Fg is equal to 340 newtons. This is nothing but weight of the beam. And then now coming to the torque applied by the pin, we have the L length, the pin is at the end, so at the length L, and then the force is P, so P cross L bar, so PL sine theta. This is Fg L by 2, this is. So 340 L by 2 is equal to Fp sine theta. Or else here he gave the this as P, so I will directly use that one, PL sine 39 degrees. L goes off, and then P is equal to 340 divided by 2 times sine 39 degrees. Okay. And then if we calculate this one, we will get the value as 270 newtons. Okay. This is the main part you have to understand. Just torque, what are the torques and how they are acting on the object. Just here, the pin is applying the torque in the counterclockwise direction, and beam is applying the torque in the clockwise direction. Okay, and then torque is equal to R cross F bar, where R is the distance between the point of application of force and the axis of rotation. So here, the beam is a symmetric object. That is why the force acts from the center of gravity, which is at the center of the beam. That is L by 2. Therefore, the torque applied by the beam is Fg sine theta times L by 2. Here it is 90 degrees. Am I right? Therefore, sine theta is equal to sine 90, and then sine 90 is equal to 1. Therefore, torque applied by the beam is equal to Fg L by 2. And then Fg is the weight of the beam that is given by the textbook as the 340 newtons. Therefore, 340 L by 2 is equal to PL sine 39. Here is the torque applied by the pin is PL sine theta, and then theta is 39 degrees. Therefore, PL sine 39 degrees, because the pin is at the end of the beam. So that we have to take the L. This is the hinge and this is the pin. The entire length will come into picture. Okay, and P is the force. Here he gave the force, he represented the force as P bar. That is why we have to take PL sine 39 degrees. So this is the P is the force, that is 270. The force applied by the pin is nothing but 270 newtons. Now we have to find out the other two forces. Horizontal component, the horizontal component of the hinge force, and then vertical component of the hinge force. Now to find the horizontal and vertical components of the hinge force, we will use the force. The sum of the forces must be equal to 0. Now what are how the forces are acting? Now if you see this one, in the horizontal direction, the hinge is applying the force in the leftward direction, and then the pin is applying in the rightward direction. Okay, so how it will be, can I do here itself so that it will be comfortable for you? So H is in the left side and then P is in the right side. You see here PH is in the right side. Now I will write sigma FH is equal to 0. That is the condition for the static equilibrium. Here the left side is H, therefore H must be equal to PH horizontal. So PH is nothing but P cos theta. And then we already found out P as 270 newtons. Therefore, H is equal to 270 cos 39 degrees. This gives us 210 newtons. Okay. Now, we will do the other one. We have to find out V. See here, the V is acting upwards, and then PV is also, P vertical is also acting upwards. But FG is acting vertically downwards. So, V plus P vertical is equal to Fg, or V is equal to Fg minus PV. That PV is nothing but P vertical. Okay, so here Fg is nothing but 340 given in the question itself. So 340 minus P vertical is P sine theta. This is the angle, so this is the opposite side, therefore it will be P sine 39 degrees. P is 270. Therefore, V is equal to 340 minus 270 sine 39 degrees. Okay, this gives a value of 170 newtons. Okay, this is how we have to do the problem. And then any doubt in this? If you have any doubt, you just keep the in the comment section. I will explain to you. Okay, put the message in the comment section. That's all. Thank you.